Okay, so welcome again, everyone, and good morning. We will start the second day of this e-motor design conference. And same as yesterday with Polestar, so our second speaker from Polestar is online again. As we said yesterday, they were supposed to join, but due to a last-minute issue, they had to cancel their trip. But fortunately, they can present online. So today we will hear from Andreas Carlsson from Polestar. He's CAE engineer in Polestar and works with Shafiq Nateg. Yeah, so I think Andreas, you can start your presentation now.
Yes, hello everyone. My name is Andreas Carlsson and I work at Polestar Performance AB. And today I'll be presenting optimization of hairpin wound e-motors for e-mobility. And I will specifically look into the reduction of AC losses at high speed and what you can do with the pins in the slot to quite significantly reduce the AC loss. So let's first present a bit about Polestar. I know most of you probably saw Shafiq's presentation yesterday, but for those of you who might not have, I'll quickly run through it. We were founded in 1996 and we have our roots in Swedish touring car racing. Volvo acquired us in 2015 and to this date we have two models produced. It's the Polestar 1, which is a hybrid and that's no longer in production and it's a grand touring vehicle, and the Polestar 2, which is currently in production and it's a fully electric vehicle. In addition, we have the Polestar 3, 4, 5, and 6 in production. And if you want to know more about those, you can look at Shafiq's presentation. So a bit about me. My name is Andreas Carlsson, and I'm 24 years old. I graduated from Chalmers University of Technology in 2021, where I studied electrical engineering. And during my time at Chalmers, I was a member of the Formula student team. And directly after my graduation, I joined Polestar as an EMD engineer. And since then, I've been working solely with electrical machines. On my spare time, I enjoy training, fishing, and working on old cars. So now onto the contents of the presentation itself. First, I will cover the advantages and disadvantages on a high level between hairpin and random wound machines. Then I will introduce a case study on a concept level, introduce you to the e-machine, the initial parallel optimization process that I like to use, and then a concept design optimization. After that, we'll look more at the detailed design methodology, and I will highlight the differences between random wound and hairpin machines and how we handle it differently. After that, we'll go back to our case study again and look at the AC loss minimization, which is a part of the detailed design that we do at Polestar. I will show you the geometry and which parameters I use. And then a trick, which is a single phase equivalent model, which will significantly speed up your simulations. And then I will show you the results from the optimization itself. And then we'll go into some questions. So let's start with the hairpin technology and the round wire technology. So with a hairpin, we can have a significantly higher fill factor. And we can reduce the DC loss, partly for that reason. We also get shorter end windings, which will both help with the losses and it will also lead us to have more compact machines. It allows us to have a stronger insulation system, and we're in complete control of the voltage distribution within the slot. So the turn-to-turn voltage we'll have much more control over. And finally, we'll also see reduced iron losses because of we're able to utilize more iron within a certain volume restriction. When it comes to round wire, we have a much higher winding flexibility. We can also reduce the AC losses. That is due to the smaller conductors, and it's less complex to manufacture because we don't need to weld every connection. So moving on to the case study itself, what I'm going to show you now, it's a 54 slot machine, 6-pole. It has 6 pins per slot, and I've designed it for a system voltage of 800 volts on the DC side, an inverter current of 770 amp RMS. The lamination thickness will be 0.25 millimeters, and we'll have a 45 SH magnet rate, and I set an arbitrary power requirement of 375 kilowatt, and it's a W rotor. So the first part of an optimization process, whenever I do anything really, especially when you have a requirement set by the system team for the vehicle, I set a hard constraint on performance and I try to maximize efficiency. That's the 2 top plots where you see we reach the torque at the given speed, but we can't reach the loss target. We're quite high above that. So, and then I start a second optimization. That's the 2 lower plots where we try to set a hard constraint on the efficiency. And then we try to maximize the performance. So there we can see that we reach 0.8 per unit on the torque. Now, the reason I try to show this is because this, you then feed back to your vehicle system team. And you try to challenge their requirements. For instance, in this case, I reduced the torque and power requirements by 15%, and then we re-optimize for the new attribute. And then you can see here that we get significantly closer on the losses. And this is very important that you don't just accept the requirements set on you by your system team, but that you feed back how you can improve by changing the requirements, because usually there are some leeway with them if you're able to get, and you're in the end able to get a better product on a more holistic level, let's say. So if we now move on to detailed design, which is a lot more interesting, I think. So if we look at the differences between hairpin and round wire, we still have our mechanical rotor design. That doesn't change. The demagnetization study you need to do, you need to check your NVH, where the performance itself may differ slightly. You look at the skewing and magnet segmentation designs for torque ripple minimization, but the real difference, it comes when we look at the thermal. For instance, you have more opportunities to cool a hairpin machine better, especially on the end winding, and you don't risk getting hot spot within your conductors, or it's not as likely to happen. The second part is the insulation system design, where you have much more knowledge of your turn-to-turn voltage, and ideally you'd measure it on a hairpin machine so you'd know exactly, but you can get a very good idea given your winding layout. On a round wire, you have to assume worst case. So depending on your winding layout, you might even see the full DC link voltage as a transient, as your turn-to-turn voltage, and then you need to design for that. That's not necessarily true for hairpin. And the final point, it's for hairpin machines, we need to dimension our conductors in a way to minimize AC loss at high speed. Whilst for a round wire, you want to optimize your conductor diameter towards a high fill factor for your given slot design. So if we look at how I try to minimize the AC loss, what you could do is that you unlock every single parameter for your individual conductors. And your targets will be to maintain performance, maintain or reduce the iron loss and DC loss, and you want to especially focus on reducing the AC loss. So you'd pick an operation point. If you're only looking at one operation point, let's say, then you want to pick one at high speed, maybe highway operation, let's say. So low torque, high speed. And I would lock the rotor design and also the stator laminations. And we would look at changing the conductor positioning, each conductor relative to one another and and relative to the slot. We had a non-uniform conductor size. And then we would also use a single phase equivalent model, which I'll show now. So a single phase equivalent model is something we have used for a long time at Polestar, which essentially is that we only model the AC loss for one phase. So you see here that we have a finite element conductor for only one phase, and the other two we use coils instead. That's a bit easier to set up. It will speed up the optimization significantly. But with the downside, you have some effect on the accuracy of your loss calculation. Commonly, you'd have 3 finite element conductors instead. But for this specific case, we reduce the simulation time per case by 6%, and the losses vary by less than 1%. Now, from previous calculations that we've done using this, there is a slight risk if the resistance between your coil and your conductor vary too much, you risk getting a circulating current. But as long as you're aware of that, and it shouldn't be an issue, and it will not affect your results that much. So now if we move on to the optimization results themselves, what we'll see is that we can reduce the copper losses by up to 15%. I unfortunately didn't have time to let this simulation completely converge, but all of these cases fulfill the constraints that I have put on it. So you can see that we can easily reach a 15% reduction in the copper loss for this highway operation point. Now, if we look more on the conductors themselves, we're going to look at the first conductor, that's the conductor closest to the air gap, and then the sixth, which is the one closest to the stator yoke. So what you would see here is that the width converges to around 0.9 per unit, with 1 being the reference. Whilst the sixth conductor, it's 0.98 or 0.99. And so here you see that the first conductor closest to the air gap benefits to be a lot thinner compared to the one closer to the yoke. And if we look at the height instead, so in radial direction, we see that instead the one that's closest to the air gap, it's slightly larger in radial direction compared to the one closest to the yoke. Now, I'd like to point out here as well that you see that none of these go above the reference, which was defined as the maximum size the conductor could have given the geometry constraints. But I would have expected it to go closer to 1 per unit. But the reason that it doesn't is because we only looked at one operation point. And for future work here, what we do is we introduce more operation. What this specific one was low torque, high speed. But in future optimizations, you would ideally introduce some low speed points where you also want to focus on efficiency. And then maybe you'd also need to introduce an operation point at maximum current, because otherwise you would risk running into thermal issues because the current density would be far too high. And then you'd also need to investigate the manufacturing constraints in detail. As you saw in my previous slide, I had individual parameters for all conductors, but what we saw from having done these optimizations a few times is that it's only really the first conductor closest to the air gap that you need to have modeled slightly differently than the other ones. So this one will give the most benefit. If you can only have that one being slightly different than all the other ones, you will see a significant benefit. But this will, of course, be somewhat difficult to build. But it would be very interesting to do this as a prototype, which is something we might look into in the future. Because, of course, we need to validate the results. So now I realized I ran through this quite quickly, but if you have any detailed questions or want to discuss technology, you can always reach me via mail, and I'm also open to questions now.
Thank you very much, Andreas, for this presentation. So yes, I think we can take some time to see if there is any question in the attendance. So yes, do you have any question for Andreas? Yes, so we have one question, Andreas. I will give the mic.
Hello, I'm Zoran Advori from Rolls-Royce Electrical, and I have one question regarding the optimization strategy you use. Have you ever tried topology optimization for the conductor sizing, or could you get different results with that?
I have never tried it personally. So I can't really say if you get different results or not. Maybe I can direct that question back to you. If have you seen any significant?
Not yet, because we are not really working with Hairpin winding. It's just out of curiosity, since it's in Jmag, the topology optimization process, and I thought that you already tried that.
No, not yet. That is on our to-do list.
Thank you.
Yes, another question.
Hello, my name is Bernd Cebulski from IAV Germany. You said at the beginning that you have separated the optimization from the rotor topology by just looking at the stator slot. This is true since you have very much closed slot openings for the stator. If the opening is a bit wider, there's a heavy influence from the rotor magnets to the upper bar in the Hairpin winding. Have you investigated about the losses of the upper bar regarding different magnet topology and maybe interaction influence to minimize the losses also by rotor topology?
To an extent, yes. We have not looked at it specifically, but if we run large optimization, it's very often a parameter that we have taken into account. The issue is often that if you, when you run your large optimizations, you don't want to have too many parameters at the same time. But if you do, let's say you run this specific one to reduce the AC loss, again, then I think I would open up those parameters as well. And investigating different rotor topologies and how they would influence this would be very interesting if we'd specifically look at this.
Thank you. Any other question? Yes, we have one more question.
Hello, thank you for your presentation. Joel Wenger from DriveTech. And my question is, do you investigate using preformed Litz wire or preformed Litz bars for reducing AC losses in the slot?
We have, that's in our on our roadmap, but so far we haven't gotten into the details of it yet. But we have discussions on introducing that.
Thank you.
Thank you for your questions. Anyone else? No, so it seems we have covered all the questions from the attendees. So thank you very much, Andreas, for joining us online. Yeah, so hopefully next time you can join physically.
Yes, I really hope so. I'm going to do everything in my power to be there next year.
Great, very good. So good luck for the rest of your day. And
Yes.
yeah, we will here continue with the next presentation.
Yes, and thank you everyone for listening, and have a nice day.
Have a nice day.